All right, so I'm going to do, we are going to start out with everybody getting on Canvas. And answering, oh, that's on. So there's this in-class graded quiz. I was typically planning on using these more sort of work through problems in class. But I'm getting a little bit discouraged by the portion of students that are in class and the ones that I see on the roster. So for all of you who are here right now, get on that Canvas website. There's a quiz down here, in-class quiz. Click on it, fill it out. All you have to do right now, we're just going to do it real quick so people that aren't here today aren't going to be able to get this. Go in and click yes on the base points. Okay, so to go in, click yes on these base points. Get it submitted. I'm not going to close it out. And basically, for being here today, you're going to get the full 5 points of in-class, kind of this additional quizzes that I'm using throughout the semester. Again, it wasn't really my intention to necessarily just use them to award. I was going to have like grade these for correctness as well. But I'm trying to really incentivize people who aren't showing up to the class because I know that that's going to be very important and it's going to be negatively correlated with exam scores. So should be able to get on the Canvas, get into that quiz, just answer the base point one, make sure you click yes. I'll kind of then get those scaled up after class to be 5 out of 5. I have a question back there.
I was gonna ask, are we just?
Yep, just click the base one so we can get it out of the way. We'll review the questions later on today. Like I said, I'm just trying to kind of incentivize being prompt and also being in class. Okay, so leave it open for a minute or two, kind of and I got some other stuff I'll talk about, and then we'll kind of jump into class. So a couple things off the top. I wrote things down so I don't forget to mention everything. I might, no, actually that doesn't apply to this class. So you'll notice on some of these like homework, so the problem set that's due at the end of the day Friday, some of it's not done in Stata, right? Some of it's like something you have to write out, or you can use comments and kind of type out your answers in your do file if you want to. You can also write them on a separate piece of paper, upload a picture of it. You can do it in Word, upload that. But you are going to start to realize with these problem sets, it's a little bit less and less work we're doing in Stata, or you might have to do some work, but then there's going to be some subsequent questions where you have to do interpretations, or, you know, it's going to be more kind of written response type of things. Okay. The first problem set was primarily just Stata commands. And so that one was, you know, it's going to look a little bit different as we kind of move forward. Okay. So, I'll probably get up the next set of practice problems. So that second quiz was due before we started class today, right? So I'll get that next set of practice problems up. We're always going to be a little bit lagged, right? So, you know, you were doing week 2, or sorry, week 2. You're doing quiz 2 and problem set 2 over that regression stuff, simple linear regression. But since then, we've been talking about multiple linear regression. We've actually talked about things that have are now better approaches than even what we were talking about before. So when you're working on these assignments, it's always going to be a little bit lagged. So you shouldn't need anything from the multiple linear regression for that problem set 2. It should simply be, you go to that files tab. Well, you just go to the home page. Everything you need should be in this regressions in class do file. Okay. So everybody got on and got that quiz done? Anyone still? All right. I'm going to then close it out here real quick. I think I had it set what time, so I want this to be. I'll give it a little bit of time to, in case I click in. All right. So with that in mind, you still have some questions over that problem set. Typically, my office hours are 12:30 to 3:30 on Monday, Wednesday. So a couple of you stop by on Monday. Those of you who are working, let me see. I'm trying to recognize faces. Yeah, there's a lot of people there, right? So I teach 2 very large 300-person sections of B251. They have an exam Thursday. So what do you think is true about my office hours this week? It's a Zoom, right? So Mondays usually aren't terrible, which is why I didn't have a room reserved. So I apologize if there's a bit of a wait. Wednesday, I know that it's going to be crazy, so I reserve a room for my office hours. The problem is there's so many 251 courses, it's hard for you guys to get in there and get questions. So if you do have questions, I'll actually be in my office tomorrow from 10 to 12. just telling the my 371 students that. All right, so if you want to stop by tomorrow or Friday, I'll also be there from 10 to 12. And I'll get an announcement up on Canvas about this. I just want to mention it in class. If you come by those usual office hours, I'm not going to be in my office tomorrow. We're going to be in a different room I have reserved, so I don't, can only get 3 people into my office, and there was like 8 or 9 at one point waiting at a time yesterday. So it becomes kind of a negative externality to the other people that have offices near me. So I've got a room reserved there, but won't have office hours during normal times, but I'll be there tomorrow, 10 to 12 and 10 to 12 Friday for you guys in my office. Okay? Is that clear? Yeah, okay. Other than that, are there any questions for me before we jump into material? So I had a question to start class. How many, how'd you phrase it? How many chapters are on the exam? So the exam, I believe, is the 17th of October. Hopefully I'm doing that from memory correctly. It's a couple weeks out, right? So we should start thinking about it. I'll get a practice exam up closer to that date. We're still going to have one more quiz. So I'll kind of hold off, give you the practice problems for those. And once that quiz is closed, get up the practice exam. It's not really like, I don't teach this class necessarily following the books in terms of chapters, right? I know the topics and the material that I want to cover related to different, centralized topics. And so here, it's going to look like we really kind of only have like 4 topics, which are review of statistics, review of probability statistics, normal distribution, simple linear regression, and then multiple linear regression. Now, multiple linear regression is going to cover like 4 weeks, right? So we had last week, this week, and really the next 2 weeks of material, we're going to be just talking about different issues related to multiple linear regression. So in terms of chapters, I wouldn't think about it that way, but basically 7 weeks, and then we'll have our exam week. Now that exam week, almost all the time, I don't promise this, but this is a loose promise. That Tuesday before the exam, the class will pretty much just be with you. We'll have covered everything, but up to that, we'll have covered all the material we need to up to that point. That Tuesday is just going to be working through additional examples, fielding questions from you guys in the practice exam. And so that exam week, that Tuesday's class will be very helpful, very beneficial. I wrote the exam, so I might have some good things to say. Okay. Any questions before we dive into the material here? Okay. So we left off with this example last class. We were thinking about athletic revenues and then the conference that a school belonged to. So this is the idea. We have multiple dummy variables. So another example could be, let's say I'm trying to predict GPAs, and one of the controls I want to use is what level are you at the university? So are you considered a freshman, sophomore, junior, senior? Just a 1 if you're considered a freshman for that freshman, 0, 0 if not. 1 for that sophomore variable if you're a sophomore, 0 if not, etc. If I try to include all of those into my regression, what is Stata going to do? We said if I have perfect multicollinearity, anytime I see that freshman variable be 1, automatically I know the sophomore, junior, and senior variables are zeros. So I have perfect multicollinearity. Now, this was this new assumption we can't be violated. So what did Stata do? Just picked out one of them, right? It identified it and got rid of it. Now, on the exam or something, I might ask you to write out a regression. How would you predict GPAs based off of the classification of the student? And you would have to write out maybe some free response on that exam. You might have to write out what the regression equation would be. You would need to know that you need to leave out one of those variables. If you write it out that you've included all of them, right? You can't do that, right? Stata won't let you do that, right? So there's some fail safes there, but I'm also going to kind of try to test your knowledge over what actually needs to be occurring, right? Why is Stata kicking out that variable? Well, because anytime freshman's 1, the other 3 have to be 0. We don't have a comparison group, right? Our slope coefficient is always belonging to the 1 group relative to the 0 group. Here's the additional change in whatever our y variable is. Well, if I don't have a control group, can't really make that statement, right? So I don't like this example, so we're just going to skip this. And I'm going to go straight to thinking about this traffic data example I have. So I'll show you kind of all the stuff behind the scenes in Stata here in a second. I think we'll start out with the results and then kind of see how did I actually come up with these regressions. So I had this data set laying around, and I think it's from the 80s. It's old, which will be important for some of the things we'll talk about later. And I think it's from Houston. I think it's a large metro area in like Southeast Texas is how they define it. So probably Houston, right? But it has all these traffic stops. And so I have a variable that's ticket, which is, did that traffic result in a ticket being issued? 1 if it did, 0 if not. I then have all these different racial identifiers. Now, we obviously could break this up into more. This is kind of a a naive like subset of different racial categories, but here in the data set, it's identified 1 if the driver is white, that white variable is 1, 0 if not. The driver was identified by the officer as black, 1, they were, 0 if not, et cetera, et cetera. And we have kind of a catch-all category, right, of other. And so if I try to run this regression, well, that other category, right, I now no longer have any group I've left out. So what does Stata do? It's like, you can't do that, right? You've got to leave out one of these variables. It will automatically omit one of these variables for me. I believe the way it chooses it, I think I might have said this last class. I think it's the one with the lowest number of observations. I can't exactly remember. You can probably Google it and figure it out. But we'll talk about, like, we don't always want to just rely on Stata for this because sometimes it's going to be important what group we leave out. So here, if I'm looking at these results, you know, okay, this is good because I am seeing some like positive and negative coefficients. So some groups are more likely to be issued a ticket. So how would I interpret this slope coefficient on black? So this is if the driver is black or not. Well, if the driver is black, relative to whatever the 0, relative to the group that was left out, other, the predicted increase in the what? So if I have a dependent variable, we said the units are probabilities. So it's an increase in the predicted probability a ticket is issued of about 0.06, or increases the probability of getting a ticket by 6%, right? Stata is always going to give us things in probability or proportion format. We can always kind of convert that to percentages by moving the decimal in 2 places. I cut it off here. But another similar thing to that would be, if I'm looking at my R squared, right? First of all, how much variation am I explaining? The proportion of variation I'm explaining in tickets just by the driver's race, 0.001, 0.1%. Not very much, right? Probably shouldn't put too much stock in these results, but for the sake of kind of the exercise, we'll kind of go through it. In fact, here, there you go, that's what I want. So, Stata kicks it out, kind of saves us, we do this interpretation. But notice, none of these variables are statistically significant at any of our conventional levels. All the p-values are greater than 0.1. So we can't actually say that the driver's race from this regression actually has any impact on whether or not they're issued a ticket. So that's good, right? That's something we want to see. But we haven't controlled for a lot of other factors, right? It is likely that there's a ton of omitted variables that are causing bias in all of these slope coefficients, right? We talked a little bit about that before as well. So let's think a little bit more about this traffic stop data, kind of touch on some stuff we talked about last Thursday and introduce some new things as well. So let's say instead, maybe it makes a little bit more sense. So I had not only the driver's race, I had the officer's race as well. Now, in general, we don't think that there's probably discrimination going on towards white individuals. Usually we think it's going to be different minority groups. And so what makes the most sense to have our base group be? Probably white drivers, right? And then all of our slope coefficients tell us, is there any type of like additional probability, increase the probability that you're issued a ticket if you belong to one of these different minority racial groups. So we're going to leave out white here because it probably makes a little more sense than leaving out that other category. Once again, Stata will do it for you, but it makes a lot more sense in the context of this example to leave out a different group. So I have this regression where I've included the driver's age, I've included all of these identifiers for whether or not the officer was each one of these different races, all of the identifiers for whether or not the driver was each one of these races, but I left out the driver and the officer being white. Right? So I also kind of did the same thing, but now I ran a regression where it was a 1-0 if the traffic stop resulted in an arrest, 1-0 if not. Okay? So I've got kind of the summarized results here, but let's just kind of do this in Stata. We'll kind of piece this together. So just as a reminder, scroll up here. I've got my global path that I'm going to set here. If you don't like using that, you can simply download this traffic data set. It's on the front page of Canvas, drag it into your OneDrive, select it, open up that data file, right? This is the actual data. It's got DTA, okay? So you can see all these different variables and we'll use a bunch of them here, okay? So now that I've got it open, I'm also going to just run this. I put this at the beginning because I think, I don't know if we'll use one today or not, but definitely on Thursday, we'll start using a lot of these free data sets. The problem is every time I open up Stata, I need to tell it to like install this package that has all this free data behind the scenes. So I'm just going to SSC and, oh, did it twice, but I'm going to just do that so I can use these, free data sets. Unfortunately, because I believe this is the case, unfortunately, because we're working on it, like every time. You exit out of and then get back on Stata through IU Anywhere, it's basically like you just close the program, so you have to do this every single time you open the program. It's a bit of a pain, but it's what we have to do. So anyways, I digress. We have this traffic stop data. There actually wasn't a ticket variable in this data set, right? So what I'm gonna do, right? A lot of times we have to create these dummy variables. The variable that is in the original data set isn't a dummy variable, right? So I had this result of the stop, and I'd have to go back and look at the code book. I forget exactly what number, there's a bunch of different numbers. If I look at the actual variable, which was result of the stop, I don't remember what 5 means. I do know, because I looked it up, to specifically, the result of the stop being equal to 2 represented just a ticket being issued. So I'm creating this new variable that's a 10 variable. So anytime I use that gen command, if I put a conditional statement in parentheses, that's creating a 10 variable. So anytime that statement's true, the result of the stop was equal to 2, which represented a ticket being issued, a 1 gets put in here. Anytime that's not true, a ticket wasn't issued, we get a 0. Okay? So I'm going to create this ticket variable, check it out. Sure enough, scroll over too far. My screen's not quite big enough. Every single time, where is that? Oh, no, it is. I'm looking at this backwards. Result of the stop, every time it's a 2, my ticket variable is equal to 1. Every time it's not a 2, I get a 0. Okay. So I've now created this dummy variable, which represents a 1 if the ticket was issued at the traffic stop. Everybody with me in that? Okay. We did this last class. I'm not going to waste time. You definitely have perfect multicollinearity if you use the same variable twice. I then had this driver race variable. Once again, it didn't come in nice where I had all these dummy variables. It was just a single variable that was equal to a different number that represented a different race, right? So the only races that it had 1 through 5, 1 was Asian drivers. And so anytime there was a 1, I created this dummy variable that put a 1 in for Asian, 0 if not. Anytime it was a 5 that identified the driver as white, 1 is put a 1 in there. If that was true, 0 if not. Right? So I'm just going to create these dummy variables real quick. You can now see, got them all there behind the scenes. So here is our very naive regression we ran, where we had a very low R squared. In fact, actually, let me rerun this because I know it's not quite. There we go. 0.0014. Really, really low R squared. We are not explaining much of the variation at all in whether or not a ticket was issued just by the driver's race, right? Once again, that's good, right? So what if instead I created all of these dummy variables for the officer's race? So now I can kind of control for what the officer's race was. Maybe I think there's like, white officers might be more discriminatory towards non-white drivers or vice versa. I'm now going to run this kind of more non-naive regression where I start to control for a lot of other factors. So here, I've still got the driver kind of race dummies. I'm also now going to include the officer's race dummy variables. I'm also going to include this 10 variable for if the officer was male, the officer's years of service. This is the number of years they've been a police officer. I'm also going to use this thing that we talked about last class, which makes this regression a lot more powerful, which is this IDOT command. So the IDOT command essentially created dummy variables for us that are going to be used in the regression for every single value of this variable. So if you have something like wage, where you probably don't want to use the IDOT command because it's just going to create so many dummy variables, and that's another set of issues that we'll touch on later on in the semester. But usually if you have something like this reason for the stop, it was like, I think 0, there was like 1 through 10. And, a 1 was they were speeding 5 miles per hour over. I think a 2 was like they were speeding, whatever is considered reckless driving, right? And then various, expired tags. I forget exactly what all of them are, but this IDOT command is going to create a dummy for each one. So essentially it's like we're controlling for the reason for the stop. So, if someone cuts across 5 lanes of traffic, probably a lot more likely they're gonna get a ticket issued at that traffic stop than if you're just going 5 over. We now can control for that, okay? So I'll run this regression where I've got a lot more additional controls. So here's all my different reasons for the stop. It left out one of them, which was the 1. I don't remember exactly what that stood for, but had to have a comparison group. I've now got my officers, years of service and whether or not they're male, my driver race identifiers, and my officer race identifiers. Now, I didn't let Stata choose for me. I chose to leave out both white officer and white driver as those 2 dummy variables to avoid multicollinearity. So if I'm thinking about now, what's the interpretation of this slope coefficient on black for if the driver is black? Well, we have a dummy variable as our x variable. It's going from the 0 to the 1 group. So the driver is considered black relative to the 0 group there represented the group I left out. So relative to a white driver, the predicted change in the probability they're issued a ticket actually goes down by 0.008, right? So this would be a result I didn't necessarily expect, right? But that's because that's the interpretation, and we now throw on the end, holding all else constant. So the thought experiment is 2 drivers pulled over for the exact same reason, right? The officer is either male in both scenarios or not. The officer has the same years of service in both scenarios. The officer is the same race in both scenarios, but in one of them, the driver is black, and the other, they're white. What is the change in the predicted probability of tickets issued? That's a lot more powerful of a statement. So when you start doing control for all these additional factors, initially it looked like before, we thought maybe there was some evidence of discrimination towards black drivers. Now, essentially, this is really, it actually works the other direction. Now, it's a really small effect, right? This is the magnitude, economic significance is very small, but it is statistically significant, right? At what levels? So a p-value of 0.017, statistically significant at the
1 and 5.
not 1 in 5, right? We only reject the null if it's less than alpha, so at the 10 and 5% levels, right? Not quite at the 1% level because we're just above 0.01. Yep. Any questions on this idea? Yeah.
Question relates to the dummy variable part of it. If you're writing out like an equation and you want to test for, like you said, whether or not the officer, the race of the officer has any effect on whether or not the driver got a ticket or not. When you talk about like leaving out, I guess in this case, leaving out a variable to test for that variable being the norm, I guess. Will the dummy variable just be the variable that you're testing for to see what the difference is?
So it's going to change the context of every example you're looking at. Yeah. The group that you leave out, it's going to be situationally specific. So in this example, to me, it makes the most sense to leave out white driver because that's probably the group we expect there not to be discrimination towards, right? And so we always want that to be kind of our comparison. Last class, when we were doing the revenues one, we said we can run the regression and then look at our coefficients and what makes the most sense to leave out the conference that had the lowest, right? So in that, it's all situationally specific, right? So there's no right or wrong way. We'll talk about here in a second. It doesn't matter which one I leave out. I can still test for differences between any 2 of these groups. Yep. It's a good question. So I then had this additional variable that was a 1 if the traffic stop resulted in an arrest. So I'm looking here, it looks like, there's a statistically significant effect. Hispanic and black drivers actually issued a ticket at lower, it lowers the probability. Asian drivers, it increases probably. So maybe there's evidence that races are being treated differently in the issuing of tickets. But if we look at arrests, controlling for the exact same controls as we used in the previous regression, this is pretty staggering to find the probability if the driver is black relative to white, holding constant all these other factors, the probability they're issued a ticket is about 0.01 higher or 1% higher. Not only is that a pretty large magnitude of effect, I mean, if I'm looking here at the other racial, 0.00, these are really small, but also for the other kind of racial categories we had, can I actually say that race being in one of these cases had any impact on the probability you were arrested? No, these p-values are all above 0.1. But for black drivers, can I say there's a statistically different, a statistically different impact on the probability they get a ticket if they're considered black versus white? Yeah, p-value is 0. This test statistic of 10 is really high, right? So yeah, I didn't find evidence that there was maybe discrimination going on at kind of these lower levels of the issuing of tickets, but I did at this kind of higher level of whether or not they're arrested. Now, once again, let's be cautious. Even though it's statistically significant, my R squared is still 0.06. So I am not explaining 94% of the variation in whether or not the individual is arrested. There's probably a lot of other information I need on these drivers to like I'd want to hold constant, right? But this kind of gives you an idea about how you can start to think about identifying what I think is a pretty important question of like whether or not we see discrimination going on towards certain groups, right? We just have to make sure we go out and try to get more data, have more things that are going to help us make better predictions, get that R squared to be quite a bit closer to 1. Okay. Any questions on that before we keep moving? Yeah.
Yeah, so is it common for like something, so we said it's statistically significant for like black drivers that they're less likely to get pulled over, but we're still not explaining 94% of the whole, of the whole thing. Does that, I mean, it feels like counter, like they point in different directions.
So think about it this way. If I'm trying to predict wages based off of your IQ is definitely going to be statistically significant. But what is probably even better, like if I try to make predictions just using that, I'm going to have a low R squared, right? Because what else influences your wages? What field you're working in, right? How many years of experience you have? A lot of other things are probably actually going to be a lot more explanatory about what your wage is, other than just your IQ. Your IQ definitely is going to impact it. Like you can't, there's definitely going to, but if when we start out with a low number of variables, it's almost like inherent. Yeah, we can have things that definitely have a statistically significant effect, but our R squared is going to be low because we've only, we're only trying to predict wages with 2 or 3 factors. We know that there's hundreds of things that probably go into that. And so the long answer is, or the short answer made long, is that we'll find statistically significant effects even if our R squared is low, right? It's just that as we include more variables, now we're going to see that R squared increase, and we might find statistical significance of, instead of 2 or 3, 100 variables. Yeah.
So the higher the R squared, the more reliable the data is.
You can think of it as not necessarily reliable the data is, but more reliable your predictions will be. Think about if I had an R squared of 1, what would be the difference between my predictions and the actual Y values? If I can explain 100, all the variation, my predictions will be the exact same thing as the actual Y values. So yeah, if I have low R squared, my predictions might be off by quite a bit. Yep. Any other questions at this point before we keep moving here? Okay. So I did want to point out, I had a question earlier about like what group I'm leaving out. So here, what if I wanted to know the difference between the probability that a black person is issued a ticket relative to a Hispanic person? Well, if I only gave you the results that we had where the group that was left out was this white driver, I can kind of think about how I could do this. So there we go. So if I had this regression and Hispanic, all the other variables we included. When I'm making predictions for whether or not a ticket was issued, I'm going to use all of these slope coefficients. And for, a black driver, this would be a 1. So beta 1 times 1 would get added in, right? However, that would mean every other racial category, those coefficient estimates get multiplied by a 0. So those essentially don't exist. So for a black driver, my prediction is going to include this beta 1 hat. For a Hispanic driver, my prediction is going to include beta 2 hat, but not beta 1 hat. So what is going to be the difference in the predicted ticket probability that they're issued a ticket? It's just going to be the difference in between these 2 coefficients. So what I could do is just go to that regression output, look at that coefficient on the black variable, look out the coefficient on the Hispanic driver variable, and simply take the difference between the 2 that now is gonna tell me the difference in the predicted probability that a black driver is issued a ticket relative to a Hispanic driver. And there, I still had my comparison group I left out was still white drivers, right? So I don't have to change the comparison group if I don't want to.
So when there's like data points of overlap, would you just remove them completely, or would you, like, how would you handle that?
So here, I'm using this example, obviously, probably a little bit not accurate, right? You can definitely be mixed race, right? And so you would belong to both. That we would have to, I'm assuming here, the way that it's coded in the data, I'm not assuming, this is the way it was coded. They only coded individuals as belonging to one of these racial groups, right? So if you did have overlap, you'd have to basically just create more groupings, right? You would have a dummy variable for mixed race of this race and that race, or, you know, whatever, you know, however you want to, however far you want to delineate kind of your racial categories. Yep. So here we're just thinking about you can only belong to one of these groups in terms of the way that, and that's the way the data was coded. Any other questions on this before we keep moving? So what I could do here is, if I looked at my regression output, and now we need the, not the arrested one, we were talking about the ticket one. The difference should be, right, negative 0.008, the difference between that and negative 0.035. So if I'm looking at this right, it's about what, negative 0.027. Right? So if I ran this regression, I instead left out black driver category. My coefficient on Hispanic should be the difference between being a Hispanic driver relative to a black driver. It should be that difference between these two coefficients. It should be negative 0.207. Well, we can actually do that. So I'll go up here, copy this regression, paste it. Right? Instead of kind of leaving out the white driver dummy variable, I'll just leave out black driver dummy variable. Now my slope coefficient on Hispanic driver should be the change in the predicted probability of being a Hispanic driver relative to a black driver, holding everything else constant. So if I run this, hopefully I see that. Oh, I accidentally ran the entire file. So we're going to go back here. Sorry. Run this line of code. We'll run all of this. Where were we at? We were right here. And we wanted to run this new regression. Sure enough, now when I include white, leave out black driver, negative 0.027. Now, obviously, there's rounding because I was just looking at the third decimal here, but that I could do it that way as well, right? Just rerun the regression, but leave out the group I now want to make a comparison to. Right? Any questions on this before we keep moving? I want to revisit. No, I'll do that towards the end of class if we have time. I think it's more prudent that we do this. So let's go back here. I basically have kind of like a summary of these results in the slides. We kind of talked through them looking at the output from Stata. You know, we found that when we had this ticket variable, you know, statistically significant effects of being belonging to different racial groups. Excuse me, but when we looked at arrests, now it kind of flipped the sign and became very statistically significant. Right. So this is just a summary of kind of what those results are. Evidence that we kind of found of some discrimination. Now, once again, our R squared was relatively low. I mean, even for the ticket one, it was like 11%. There's still probably a lot of other control variables we need to add in. So we likely have a lot of what we call omitted variable bias. Right. So even though we found kind of Asian drivers are more likely to be issued tickets at statistically significant levels, right? Maybe we've got some omitted variable bias going on there. I'll go through what I think is a better example of omitted variable bias. So instead of focusing on the race ones here, let's think about if I ran a regression and I'm trying to predict whether or not a ticket was issued. And I'm going to run a really naive regression where I first start out with just a 1-0 variable of whether the driver was male or not. Right? So if I were to run this regression, right, I'm going to come up with some slope coefficient estimate. Right? So this was just a 1-0 variable. This was just a 1-0. So how would I interpret beta 1? it would be the predicted increase in the probability of seeing a ticket being issued at a traffic stop. If the X variable is 1 relative to 0, or if, I put driver, sorry. If the officer was white or male relative to the officer not being male. Right? So sorry, I wasn't talking in writing. Didn't want driver to be male, the officer being male. Right? So if I run this regression, kind of have that traffic data pulled open. What I'm going to see is it looks like male officers write tickets at a lower probability. Right? However, let's think about what omitted variable bias might exist here. Right? One of the other variables we had in that data set was kind of officers' years of service. Right? So if I leave this variable out of my regression, right, I can think about the bias that I would see. So I'll find the actual effect of the officer being male, but I'm also going to have this additional bias component, which we said would be the effect of this variable that we left out times the covariance between that variable we left in and the variable we left out over the variance of the variable we left in. So I'm going to write this out in the context of our example. So the slope coefficient we see on whether or not the the effect of the, gosh, I'm keep writing driver. What am I, why am I so focused on drivers today? So we've got officer being male, right? I'm going to find the actual effect of the officer being male, but also the effect of kind of years of service, right? Times whatever that covariance is between the officer being male and years of service. So I ran out a little room there. And then the variance on whether or not the officer is male. So if we don't have the data, we can often go through this thought experiment and actually put a sign to this bias, right? So here, if I had included in my regression the officer's years of service, and this is where, if I asked you this on like an exam or something with open-ended question, you know, you could actually explain this 2 ways and be correct. So there's probably one, well, I already know what the answer is, but I think that this is, you know, this was my intuition going into it. If you think that you included this years of service, the longer an officer is on the job, do you think they issued tickets at a lower or higher rate? So that was my intuition too, right? When you first start out, you probably feel like you got to prove yourself, right? You're this young gun, you want to make a name. I'm writing on being this hard ass, right? And then the longer you're on the job, you don't care about that as much. You're also able to identify like, okay, this was actually an honest mistake by this individual. This is something that I should be not wasting my time on. And so probably the longer you're on the job, I would expect, right, that effect of the years of service is likely going to be that you're less likely to write a ticket, or a negative effect, right? So if you had told me that you thought for whatever reason that, you know, it was the other way, that, you know, I'm on the job longer, I just start to hate everybody, so I start giving everybody tickets, that's okay, right? That would be another kind of, you would think about it. But here, this would be kind of my intuition. So as long as you explain why you believe that relationship is what it is between years of service and ticket, I would kind of grade this problem accordingly, right? So I know that I've got kind of this negative effect that I think is going to occur here. Well, this was a data set from the 80s. What do you think is true about an officer with 30 years of service? Think about what that would mean. If they were not a male officer, that means they started being a police officer as a female in the 1950s. How many women do you think were police officers in the 1950s? Not many. Our society looked a lot different, right? So if we're looking at 1980 data, I mean, we're going to see any officer with years of service of 30 is probably male. Right? If there's any female officers in this data set, they likely aren't going to be able to have as many years of service, right? They were essentially kind of kept out, right? Not, you know, it's not like technically there were some, but you know, society as a whole is kind of pushing them out. So I would think that for higher years of service, it's going to be more likely the officer in the data set is male. So this covariance between the two, probably positive. Now, my variance here will always be what? In terms of sign? always positive, right? Variances has to be positive. So I've got a negative times a positive over a positive. The sign of my bias here is going to be negative, or the estimate that I see from Stata for my naive regression is going to be a little bit too low. Now I say too low here. If the effect was negative, it actually would be like making it a larger negative value, but it's going to decrease that effect that I'm seeing. So maybe instead of saying low here, this negative bias is going to decrease the value of that slope coefficient I'm seeing if I do run that naive regression and I don't include this important omitted variable of years of service. Any questions on this idea? So we've looked at examples here, but this is another example. So I can kind of put a sign to the bias without data. Once I actually have the data, I can run this regression, obtain beta 2. I can look at the covariance between these two variables, and I then can put an actual size to that bias, not just a sign. So that's what we're going to do next. So we're going to go back to that Stata file. Here I've got, my naive regression. It looked like male officers, the predicted probability they write a ticket relative to non-male officers is about what 0.03 lower in terms of probability, so 3% lower. However, we just kind of talk through, and I have it written in kind of comments here. Here would be our bias. Well, what do I think the covariance is between these two variables? I can look at that, right? So I come down here, I run this regression where I now say, okay, I actually have officers' years of service in the data, so I don't need to run that naive regression. I'm going to go ahead and just include it. What happened to my estimate? It went from negative 0.034 to negative 0.001. So what's approximately the size of my bias here? It's going to be what, 0.033 or negative 0.033, right? That was existing. Now I can actually find that a different way. Let's say that this years of service variable didn't exist in this data set, but I had another data set where it did. So I could actually figure out what the bias was by then running a regression, right? From this other data set where I include years of service, and here I've got that slope coefficient on years of service, or in the general format, right, that beta 2, right? So the variable we left out, here's what the effect of it would have been on probability they wrote a ticket if I had included it in my regression. I can also use this correlate command, right, and then comma covariance. This will give me the covariance between these two variables, right? That was the other thing that I needed, okay? So I'll run this. So the covariance between if the officer's male and years of service, sure enough, it ends up being positive. And also just to kind of point out that relationship we thought of years of service and issuing tickets, it is negative. So they write tickets at lower rates the longer they're on the job. Okay? So we got the signs right. Now it's just a matter of how do we determine what the size of the bias is? Well, I now have that coefficient on the omitted variable. I've got my covariance. The only other thing I needed was I was dividing by the variance of the variable that I did include, which was whether or not the officer was male. So this covariance matrix, what is the covariance of officer being male with officer being male? That is really just telling you the variance of that variable. So like the diagonals here, those are just the variances of officer being male and officer's years of service. So in our original naive regression, we had whether or not the officer was male. So this is the variance value that we'll need. So got that, we got everything we need now. We've got what that beta 2 value was, covariance, the variance. It's just a matter of plugging it into that bias equation. And I think we end up, you can kind of prove this to yourself. So copy this, paste it into Excel. Sure enough, I get about negative 0.033, right? Which is exactly what it looks like if we're just comparing the two coefficients, one from the naive regression and then one where we include this important omitted variable. Any questions on that? I know we've worked through some other kind of examples like this, but kind of seeing the actual data I think is also kind of helpful. I can use these correlate commands. Any questions? Okay. All right. So we won't waste time on this. Where are we at? Yeah, we got 30 minutes left. So what I then want to go do is kind of go to the next topic. All right. So we talked about perfect multicollinearity. We can also have imperfect multicollinearity, right? So what does this look like? So this is going to be variables that are highly correlated, but it's not exactly one-to-one, right? So this would be something like, it's a goodie. So we could do the officer's years of service and the officer's age, right? You can't have 20 years of service if you're only 18, right? Even if you started from birth, right? So we know that, you know, different officers are going to have different intercepts, right? When they started the job, but every year older you get, once you have the job, automatically your years of service is also going up by 1, right? So they are still functions of each other, just not perfect, right? Because some officers start at different ages, right? So we've got not perfect linear functions, but some function of each other. So here we'll kind of represent that. So let's say I have these two variables that I think have some imperfect multicollinearity. It would have to be that this first variable is some function of the second one. So in my example, like every time age goes up by 1, automatically years of service would go up by 1. However, every observation is going to have kind of different, you know, intercept values there. Right? So I could think about when I'm running this regression, it's almost like if I plug this equation up into here, beta 1 is actually going to be telling me like the effect of beta 1, alpha 1. So it's the effect that's coming from the second variable through the first variable. It's kind of weird. The interpretation isn't quite clear, right? So with this imperfect multicollinearity, you know, these coefficients aren't going to really be very useful, right? And what's going to end up happening is at least one of our estimates, that can be both, but at least one of our estimates, if we have imperfect multicollinearity, is going to see an inflation in their standard errors, right? So let's think about what that means. So a little bit of a kind of review, and maybe you're getting tired of seeing this, but I know some people are still having kind of trouble grasping some of these concepts. So if I'm calculating a test statistic, when we're looking at sample means, that was simply take the sample statistic you're looking at, subtract the assumed true population value of the statistic, and then divide by the standard deviation, right? So kind of behind the scenes here, I'll hold off on that. So when I'm calculating a test statistic for my slope coefficients, what's the sample statistic I'm looking at? My slope coefficient estimate. What's the assumed true value? We always assume there's no effect or 0. So I essentially can ignore this. We said we can think of this as like the standard deviation of our slope coefficient, but what's the term that Stata uses that we want to use in general? Not a standard deviation, but it's a standard error, right? So standard error, right? To find a test statistic, we simply look at the output, take the slope coefficient, divide it by the standard error. Okay? So if my standard error, because of this imperfect multicollinearity, is going to be a little bit higher, what's going to happen to my test statistic? My denominator is larger. This fraction will go down, right? Dividing by a larger value. If I'm thinking about a smaller test statistic, how do I find my p-value? Well, it's going to be the area in my tail, and we had two-tailed tests, so times 2. If my test statistic is smaller, what's happening to my p-value? So if I'm going from a test statistic here down to here, my p-value is going up, right? That area in the tail is much larger. If my p-value is larger, I'm more or less likely to reject the null. My p-value is larger. When do we reject? If it's less than alpha. So if this is getting larger, it's less likely that my p-value will be below alpha. So less likely to reject here, right? So anytime we talk about things impacting standard errors, we can trace this all the way down to, is it going to make it more or less likely we can reject the null? Well, here we have an issue. If we know that our standard errors are going to be inflated because of this imperfect multicollinearity, it's going to be less likely we can actually reject the null for that variable, right? It's going to be less likely we can actually say we're rejecting there's no effect and that we actually found an effect here. So this is going to be an issue for us, right? So how do we solve it? Right? We got a couple ways. So here, if we think about, I already kind of gave this example, like age and experience, or officer's age, years on the job, or years of service. Those two things are being good examples of imperfect multicollinearity. So I thought of another one, which was age and so we have this example where maybe I'm trying to predict wages based off the individual's IQ, their age, and their experience on the job. Well, we know age and experience in the job, I can't have 20 years in the job if I'm only 20 years old, right? Because I'm not working from birth, right? So I know there's going to be some direct relationship though, that once I start to get a year older, I can have an additional year of experience on my job. I know that those are imperfectly kind of multicollinear. So my animations are a little bit out of order, but if I run these regressions where I just include one of them at a time, so here I'm trying to predict wages using IQ and experience. Looks like it's pretty statistically significant, right? Not quite at the 1% level, but 10 and 5 for sure my p-value is less than that, the alpha of 0.05 and 0.1. If I then include IQ and only the age variable, looks like age is statistically significant, has a positive impact on predicted wages. So if I run these individually, it looks like I've got evidence, both of these things matter. Both of these things I can reject that there's no relationship between them and wages, or said differently, I found strong evidence that there is a relationship, that they are good predictors of wages. The problem is, if I run these all at the same time, right, here's kind of the output that I get, right? So I look here, can I say that age has a statistically significant effect on predicted wages here? Well, the p-value is basically 0, so yes, right? I can reject that there's no relationship. However, what about experience now? Well, notice my standard errors. So where are we at in experience, right? My standard error relative to what it was before is now inflated, right? So I've got higher standard errors, which led to a much higher p-value there, right? So I've got this higher p-value. It's less light. I can't nowhere close to being able to reject a null here. But inherently, I know that experience on the job should be a good predictor of wages. Like I know that this can't be right, right? Well, the reason why is because I've got this imperfect collinearity going on, right? So what do? Right, I've got 4 solutions. 3 of them are really not worth talking a ton about because the first is you do nothing, right? So if I go back here, you know, if all I'm really concerned with is the relationship between IQ and wages, and I just want to try to control for as many other factors, this is still controlling for these other variables. It's just that the estimates on those variables aren't really as accurate, aren't as useful, right? But if what I really am concerned with is just the relationship between IQ and wages, and I want to hold these other factors constant, I can just do nothing, right? I'm not really making, you know, not focused on the age, experience, wage relationship. I just want to be able to hold constant those factors. So you can do nothing. But if you are interested in what the actual relationship is between experience and wages, that doesn't work, right? So sometimes we'll have redundant variables. So in this case, it's not really quite redundant. Maybe you could argue it is, and you could just leave one of them out. But I'll give you a better one of a redundant variable. So when I open up class thinking about dummy variables, if you're a freshman, sophomore, junior, senior, what if I had that information in my data set and I was trying to predict GPAs? But I also had the total number of credit hours taken. Well, the only way that you get that classification as freshman, it's not based off of you've been here 1-2 years. It's technically based off of how many credit hours you have. So those 2 things are going to be imperfectly correlated, right? They're redundant though. They're both trying to control for the same thing, which is how long you've been at the university. So in that case, if I have some variables that are redundant, I would just want to use one of those, either the dummy variables for your classification or just your total credit hours, right? So it's kind of hard. This is a little bit situationally, you know, specific in the context of whatever 2 variables we're looking at. But if we have redundant variables, we can just leave one out. We can also increase the sample size. So if we increase our sample size, it can solve this issue that we're going to have large standard errors in one of our estimates, because I'm just going to write this out again. Here, if we go back to thinking about sample means, we have this, our test statistic for our slope coefficients is going to be this, right? Behind the scenes of this calculation, right? We had like the square root, a bunch of stuff in our numerator. Remember, for these, we're not actually dealing with the population data. We're actually only dealing with sample data, right? So I was dividing by n-1 when I was calculating the standard deviation for sample data. It's the same kind of idea. We didn't really focus on it much. I think I had it in one of the earlier slides. but the way in which this standard error is calculated, there's a bunch of stuff in the numerator and then an n-2. Okay? So behind, it's kind of very similar when we're dealing with sample standard deviations, n-1 or n-2. So if I can increase my sample size, what's that going to do to my standard errors? So if this denominator is getting larger, the fraction as a whole must be getting smaller. The other scaring me. If you divide by a larger number, the new number is smaller, right? So I'm getting smaller standard errors. Well, remember, the imperfect multicollinearity was increasing that standard error. So by getting this higher sample size, I'm kind of combating that, right? I know the standard error is going to be inflated because of this imperfect multicollinearity, but if I can go out and get more observations, I can combat that, right? Drive that standard error down, which then does what to my test statistic? So smaller denominator increases it. If I'm increasing my test statistic going further out into the tail, what's happening to my p-value? Smaller. If I have a smaller p-value, am I more or less likely to reject? So if it's a smaller p-value, it's going to be more likely it's less than alpha. Yep. So you can always kind of trace changes through, always kind of through that test standard error, test statistic p-value, and kind of determine, okay, if I get higher sample sizes, it actually makes it more likely I can reject the null, right? I'm kind of pushing back against the fact that imperfect multicollinearity made it less likely I could reject. Okay. Is that any questions on this before we keep moving here? All right, so the fourth and final thing is more interesting, which is we can, because sometimes we can't get more data, right? This is great if we can go out and get more data, but sometimes it doesn't exist. We can actually transform two variables. So I'll go through one example and we'll kind of look at one in Stata. So let's say I was trying to predict, I don't know, some type of like the number of deaths from some disease. It could be COVID, it could be pneumonia, whatever it is. Well, I know that if I run a regression with GDP and population as predictors, the higher the GDP of a country, what do you think is happening? Is it more or less likely that they're going to see higher numbers of deaths from these diseases? Less likely. So we know there's probably a relationship there. Now, population, if I just have more people, what's going to happen in the number of COVID deaths I see? It's going to be higher. If I've got 100 million people as opposed to 2 million, I'm going to have more deaths. So if I include these, what's also going to be true is there's actually some imperfect multicollinearity going on. Because as I expand my population inherently, I have, I'm having more man hours, I'm having more resources to put towards production of things. I'm automatically going to see increases in GDP. That's why countries, back in the day really like to push population growth because inherently they know that can help them increase their GDP. Right? So we know that there's going to be some imperfect relationship that exists between these two variables. So what can I do? I can also transform them to create a new variable, which is GDP per capita. Now I can include that into my regression. It's essentially still controlling for GDP and controlling for population, but it doesn't kind of have this issue where it gives me these inflated standard errors on one of those variables. Okay. So I've got another example. It's a little bit more fall-ish. So I'm gonna go down here. Didn't have my file path set correctly, but once again, you could go to Canvas, that QB salary data, download it, move it over into your OneDrive. I had all those files up there. I think I got them up there on Friday, so I'm always trying to get those up well in advance of class, so the next week you can kind of have those files on your OneDrive. I have this QB salary data, and I don't know, what does it look like? It's got a bunch of different quarterbacks. I think just quarterbacks here, maybe not. Yeah, just quarterbacks. And then I've got their total guarantee, the total value of their contract that they signed. I've got a bunch of different statistics of them. I've got their age somewhere, right? So let's think about some kind of basic regressions here. Let's say I'm going to run these two regressions. One, where I'm looking at, well, how does the total value of these quarterbacks' salaries impacted by the number of completed passes they have over the season? And then what about the total number of attempts? So I can run both of these. So you can think about it here. Higher number of completions, this is a more successful quarterback. Sure enough, we see a positive effect. More attempts, I'm using that quarterback more. I might, they matter more to the team. I'm willing to pay them a higher value, right? A higher salary. And so, although these aren't quite statistically significant, they're pretty damn close, right? I mean, we can't say this with 90% confidence, but we could say that they are having an effect at the 85% level, which is still pretty high level. So I'm looking at this result, I think, okay, both of these things look like they're somewhat decent predictors of the total value of this contract. The problem is, if I try to run them in a regression at the same time, why are these imperfectly multicollinear? I can't complete 20 passes if I only have 10 attempts, right? So inherently, completed passes are going to be a function of the number of attempts that I have. Right? So if I try to run this regression where I include both of them, notice not only did one of their standard errors increase, that's like the best case scenario, is only one of the standard errors is impacted. Both my standard errors on these variables now is greatly inflated. I can't, and I pointed at the p-values. The standard errors are larger, leading to higher p-values. So I can't reject it at any level now. I can't even say this with 50% confidence. So what do I do? Right? Well, I could do nothing. It doesn't really help me out a lot here. These aren't really redundant variables. They are measuring different things, right? The number of attempts is measuring something very different than the number of completions. That doesn't make sense. I can't create a new NFL and go out and get more quarterbacks, right? There just is what it is. So I can't, option 3 doesn't work. So what am I going to do? I'm going to create this new variable, which is the completion. It's not technically percent here. I'm calling it percent. It's going to be the proportion, right? Or essentially the ratio of the number of completions to the number of attempts. So I can kind of create that variable. Now I'll run my regression using this new variable, which was just some transformation of the two. Pretty highly statistically significant, right? And I'm now using this one variable able to control for both completions and attempts, right? Because that's how I was creating this variable. And I can start to throw in additional control variables here. And now I don't have any imperfect multicollinearity going on. Okay. So this is going to be the solution that in practice we use most often, right? The other ones are like, yeah, it's great if we can go out and get more data. That's not usually the case. If they are redundant, okay, we got lucky this example, like I had kind of 2 measures of the same thing, but here that didn't really apply for us. Okay. Any questions on this before we keep moving? What else do I want? Oh, I know what I want to say here. So I also had this, I wanted to make sure we do this. I don't know if I did this with your guys' section. I think we might have had a little more time than the other, but I wanted to make sure I reviewed it because we're going to use it next class. So I just want to review the command. If we didn't talk about it, I'm introducing it. If we did touch on it, I'm reviewing it a little bit. So anytime I run a regression, I have this command predict I can run afterwards, which will essentially give me my predicted Y values. So if I run this predict command after I run my regression, it will give me the predicted values. And I put TB here just to make it a little bit more obvious. It's going to give me the predicted total value of that quarterback's contract. So we have the actual values, the actual Y values in our data set. Here, this is going to use my regression results to predict those Y values, right? Or remember, Y hat. So if I run this command, it creates this new variable, which is my predicted total value. Okay. Now these are really large. Remember, e to the 7 means move the decimal 7 places to the right. So I can do that. And then manually, what I could do is then say, okay, look. Actually, I'll call this error term manual, right? So I want to, create this. Oh, come on. Let's make the visual easier for you guys. There we go. So this error term, well, I now have my predicted Y value. I have the original Y values. I would just take the difference between the two, and that should give me my error term for every single observation, right? So I'll generate that, go look at the variable. Sure enough, my error term, it was just taking the actual, where is that? Over a little more. Actual total value, subtracting that predicted total value, and telling me the difference between the two. So notice for some quarterbacks, my errors were positive, for some of them it was negative. We said one of the assumptions that we needed for our regression results to be blue, or best linear unbiased estimators, was that the expected value of this error term should be equal to 0, right? So here, how could I find the expected value? That's just the mean. So I'm going to just summarize this error term that I created. Just the mean here, not quite 0, right? So it's probably evidence that I need to include some additional control variables, right? It's a pretty naive regression, right? I only had completion percentage as my predictor. It's probably that's not going to, I have a lot of omitted variables. This isn't going to kind of meet my requirements included here. Right? So this is just one way we can check kind of using that predict command. Also, instead of doing this kind of manually, you can kind of just use this predict command and then put comma residual. This will essentially not give you the predicted y values, but it'll calculate them behind the scenes and then calculate your error term. So if I do that, notice it's giving me the exact same value, right? So I can do it either way. The manual way, just more time, right? Once we start getting used to this predict command and then putting kind of comma residuals on the end of it, that's a really nice, easy way to calculate this error term, right? And then we can kind of check to see, is the expected value of that error term kind of given these x values, is it equal to 0? But we'll use this predict command. We'll start using it more next class. So you'll kind of see it down here. So we'll talk a little bit more about that next class, but I wanted to kind of introduce it today.
Could you predict for like a certain function rate?
Yeah, so here I'm going to do this here. That predict command, we'll talk about it more next class. You can use it to make different predictions for what the predict command does is it's using the actual values from your data set. So it can only make predictions for values that show up for an observation. If you want to make predictions for values that are like a hypothetical, can't quite, but we have ways of doing it, which is what we'll get to next class. Yep. But yeah, that predict command can only make these predictions for actual combinations of these variables that exist in the data set. Okay. Any questions? So like I said, we'll just introducing this predict command. We'll really kind of hammer it more on Thursday. So the beginning of class started out with this quiz, but I want to kind of walk through it because the questions I actually created for a reason. I think they're helpful. Like I said, my intention was more so to use these in-class quizzes to like have you might be able to get them right or wrong, talk to the people around you, but I'm really trying to incentivize attendance and kind of being prompt on time. I'm still seeing a significant portion of people not here. So maybe moving forward, we'll have this be a little more of like collaborative kind of work during the actual class, but I don't know, I bet I was feeling mean towards the people that aren't here today. So let's say I had this question first, where I've got college GPA and then this dummy variable of 1, 0, whether or not the person was working a job while in college. I also had this important omitted variable, which was parental income. If I don't include that variable, what bias is it going to create in my coefficient on working a job? So let's think about this. So I'm going to see this slope coefficient estimate on whether or not they worked a job. It'll have the true effect on college GPA of working while you're in college, right? But it's also going to have this additional bias component, which is the slope coefficient associated with parental income. If I had included parental income in my prediction or in my regression equation. So here we had what? College GPAs. We included whether or not they worked. And what if I included, I'll just call this PI for parental income. And this was kind of like our beta 2, but here I'm just kind of putting the names to it. I think. We then said the other part of the bias was going to be the covariance between the variable I included and the important omitted variable I left out. Divide that by the variance of whatever variable I included. Right? So here, if I had included parental income, what do you think is probably going to be its effect or the changes in GPA that it would predict? So if parental income goes up, you think it's going to have a positive or negative effect on college GPAs? All right, or we had a lot more resources available to you growing up, maybe attended better schools, maybe even private schools. And so we're thinking that when this goes, up, so does this. We've got a positive, oh, sorry, I wrote the wrong one. I've got a positive effect of parental income on college GPAs. Now, that covariance between parental income and whether or not you work in college, once again, this should be, I think, an easy one where you can't really tell a story the other way. Your parents have more income, or you think you're more or less likely to work while you're in college. Probably less likely, right? You don't have as much need. So I've got a positive times a negative over a, what's always true about the variance? Positive. So here, I've got a negative bias, right? This bias component here is going to be negative, okay? So I'll try to use examples like this when I actually ask you questions, where it seems like, very obvious. I can't think of a story where you would argue parental income is gonna actually decrease your college GPAs. I don't know, maybe more of a slacker, maybe there's a way that you could, but, in general, and I'm asking this on the exam, I'll kind of tell you, assume this is the relationship between these two variables, and then you just kind of put a sign to that bias, okay? Any questions on this one before we kind of keep going here? Okay. What if I had that QB, actually, I had QB salary, I had other salaries as well, just in a different data set. So I've got every single different position on a football team, right? I left out the position of center, right? So the guy that snaps the ball, right? So here, if I wanted to know what the difference between a running back and wide receiver's predicted kind of contract value is, how could I find that? Well, all of these slope coefficients, these are all dummy variables, right? So it's just the observation, the individual was a punter. Here's the predicted change in their total value of their contract relative to a center, the group I left out. So if I want to know instead the difference between running backs and wide receivers, what do I need to do? Just find the difference between those two coefficients. Now I could rerun the regression, include center and leave one of them out, right? That would kind of give me the same value. But if this is all the results that I have, all I would do is kind of look at the difference between wide receiver and running back here. I would kind of, this looks like it's going to be about 2 million, if I'm looking at this correctly. So simple as kind of taking those, just like we did with the ticket example in the different racial categories. So if we take that difference, it should be about negative 2 million, right? A little bit different, but pretty close. I was rounding pretty egregiously.
Would you take, to calculate that, would you take if you're looking for the running back and wide receiver, would you take the running back and subtract the wide receiver value?
Correct. Yep. Now, here, just isn't a question here, but what would the constant represent here? This would be the average salary of the group I left out, right? Because if the group I left out, if it is a center, all of these are equal to 0, right? So all of these get multiplied by 0 in my prediction equation. The constant is going to be the average starting salary of the group I left out, center, right? Or in any other example, the average Y value of whatever group you leave out. Okay. All right, so we're going to end. I think that was the only. Oh, this one we had one more. So what's another way I could get at this? I could have left out running back and then looked at my wide receiver slope coefficient, or I could have left out wide receiver and looked at my running back coefficient, right? I can't leave both of them out. Then I'd have like my comparison group is actually 2 different positions, so that doesn't make any sense. Now we haven't learned it yet. I put this in here because I wanted to kind of touch on it. There is actually a way, and I think someone asked the question earlier, I can tell you the difference between the running back and the wide receiver using the method we just did, but I can't tell you if there's a statistically significant difference between those 2 coefficient estimates. That's something that we'll talk about a little bit later down the road. I don't know about Thursday, but I think next week that'll kind of pop up, okay? You'll also see in the slides, I've got one more minute here before we all kind of get out. There's not much left here. There's a lot of blank stuff. That means I'm probably going to be doing a lot of like additional examples, doing a lot of work in the dot cam. I'll state that. So Thursday's class might be a good one to be present because that doesn't get recorded, right? Other than that, I will see you guys on Thursday. Make sure that problem set's due Friday, so make sure you start